This evening is going to talk to us about maybe the most famous equation in the whole world, E equals mc squared. He's going to talk to you about how it got that way, and maybe more importantly, how all of us lay people can actually understand what Einstein had in mind when he wrote this down. So I think without further ado, I'll turn the evening over to Gerry.
Hey, thanks, Bob. It's been a great pleasure for me knowing Bob also. Actually, probably the reason that I'm here doing this is entirely due to Bob. His energy and enthusiasm for this idea of getting oldsters like myself to try to communicate physics to younger people was really what got me involved in this. And in this particular subject, I was doing some mentoring at Monte de Sold, trying to teach a young man special relativity. That led me back to look at some of the older works that Einstein had done, and this amazingly simple way of showing E equals mc squared I found, and it's just embarrassing that I didn't know it, and I am surprised to find that a majority of my colleagues don't either. They think that proving E equals mc squared is really a very difficult thing that involves your getting involved in special relativity. And I want to show you that that's not necessary. So let's see, I got some hardware I've got to contend with here. So let's start. So what's going to happen tonight? Well, what I hope is we're going to see a simple way to prove E equals mc squared. And, you know, simple is, of course, always in the mind of the beholder. I spent most of my life when I taught teaching graduate students, so we just have to see whether I've really learned how to make things simple and clear. Now, as Bob said, E equals mc squared, I think, is the best known equation in human history. You say E equals mc squared, and people say, oh yeah, sure, E equals mc squared, and it's not entirely clear that either the speaker or the listener knows exactly what's going on when you throw that equation around. And of course, it's intimately associated with both Einstein and nuclear energy, and a somewhat darker way with nuclear weapons. Now, the amazing thing about this, it's a proof of an example of how simple but very clear thinking produces an important result. Einstein did this in 1905, and it was really a result of pure thought. He didn't really have recourse to any experiments. He just sat down and thought about this problem. Maybe we'll see what led him to think about it, but in the course of it, it's just a marvelous piece of logic. So what does E equals mc squared actually say? Well, at the most primitive level, it says we got this letter E, and we put an equal sign on it, and put an M there, and then C squared means you multiply it by C, and then by C again. Of course, these things actually have meaning, because they are not just abstract mathematical, it's not an abstract mathematical equation. It says that a quantity E, that's energy, is equal to mass times the velocity of light squared. And you're going to see the velocity of light is a really big number, and that big number is really what drives what's going on. And as I said, E equals mc squared actually applies in the real world. That is, it's an equation about statements of things that happen in the real physical world. So in order to give it meaning, it's got to have some units. So we have to know, how do we measure energy? How do we measure mass? And how do we measure velocity? So let's give a look at that. And you need to do it in a consistent set of units. You know, I mean, if you say to somebody, he owes me 100, it makes a lot of difference whether it's $100, $100,000, $100 million. So we got to get those, the units straight that actually work out and correspond to what makes this expression actually true and consistent with what we observe. So energy is measured in a quantity we call joules. You may be more familiar with a watt, which is your light bulb, which is a joule per second. And mass is measured in kilograms. A kilogram is a quantity that if you took a kilogram of mass and weighed it here, it would weigh about 2.2 pounds. And the velocity of light, when physicists deal with it, we measure it in meters per second. A meter is a little over 3 feet, and you sure know what a second is. So just to give you an idea of what these things are in quantities you're probably more familiar with, a joule is the amount of energy, or you can call it work, that you have to do to pick up 3/4 of a pound 1 foot in the gravitational field. Okay? So that's a joule. Now a kilogram, as I said, is a mass that weighs 2.2 pounds. And the velocity of light is 3 times 10 to the 8th meters per second. That's 3 times 100 million meters per second. So it's it's incredibly fast. In fact, it's the fastest thing we know. It's amusing to think about it, but no matter how fast you go, if you were trying to chase light, you would always find that it kept going with velocity c. It's one of the consequences of special relativity. We don't need to know that for tonight. I just give you that for free. So this 10 to the 8th meters per second is 10 to the 9th feet per second. Or if another way, this would be a scale where the velocity of light could be 1. That is, if we measured light in feet per nanosecond, that's where a nanosecond is 10 to the minus 9 of a second. It travels a foot in that time. That would be 1. Or another units you're more familiar with are miles per hour, and it's 6.7 billion miles an hour. So light is fast. Nothing can be faster than the velocity of light. So just a few things to give you a feel for it. This isn't part of the proof. This is just probably to show you why E equals mc squared is so important and held in such esteem in the world. How much mass would have to be converted to lift 3/4 of a pound 1 foot? So that's how much mass do you need to create a joule of energy? I save you the trouble of doing the arithmetic. It's an incredibly small number. In fact, I wouldn't even know how to say how small that is. Now, if we multiply this thing by 1,000 so that the 3/4 of a pound becomes 750 pounds, and I want to lift that 1 foot, you can see, gee, that's something that takes a bit of work. It only takes 3 times 10 to the minus 13 ounces. And now if you multiply it by 10,000, then we're trying to lift something that's the order of a heavy truck. Lift that 1 foot, and that only takes 3 times a millionth of an ounce if you could convert mass to energy. So it's a remarkable thing. So suppose we had a pound of mass and we could convert that into energy. What would we get out of it? So I just did a little arithmetic. There's, oh my goodness, I better go back. Yep. Too many buttons, Bob. So this is the 2.2 kilograms that a pound is. So it's 1 over 2.2. And that's just multiplying now by the velocity of light squared. So you get something like 4 times 10 to the 16th joules. Now, that's a big number. What does it mean? So I tried to convert it to something we could get a feel for. An average home in Santa Fe uses about 10 to the 8th joules per day, or 365 times 10 to the 10th joules per year. So this pound of mass, if we could convert it into energy, could apply the electrical energy needs of over 1 million households for a year. So you can see there's just an incredible potent energy content in mass. Of course, it's not easy to convert a pound of matter into energy. That's why you would end up collecting a good deal of money if you were able to do that. And I thought it was interesting to look at a couple of more consequences of E equals mc squared. What goes on in the sun? So the sun radiates energy. It's pretty straightforward to figure out how much energy the sun radiates by seeing what we actually measure here on Earth. And it radiates energy at this staggering number, 3.6 times 10 to the 26 joules per second, which means that it's actually consuming 4 million tons of mass every second to generate this visible energy. So that might make you a little nervous that the sun is going to run out of fuel. However, the sun has 6.6 times 10 to the 26 tons of mass. So it's a long time before we run into any serious problems. Now, just as I mentioned, a little bit more on the darker side. Suppose a megaton, which is a really big nuclear explosion, was created. That's what it's worth in joules, 4 times 10 to the 15 joules. And look at how much mass is converted into energy. It takes 1.6 ounces of mass, and you've got a megaton explosion. Okay, let me say a few words about the discoverer of E equals mc squared. It's Albert Einstein, born in 1879 in Ulm in the state of Württemberg in Germany, of Jewish parents. Here he is when he's about your age. This is a picture of Einstein at the age of 14. You know, he looks like a regular guy. And in fact, he wasn't really such a great student, or it was nothing that was, that seemed to really catch people's attention until 1905, when Einstein is now 26 years old. Physics, we call this year, is known in physics as Annus Mirabilis, which is Latin for the miracle year. And in that year, Einstein solved 4 of the most important problems in physics. And nobody really knew who he was. He was working in a patent office in Switzerland. He had had some formal schooling, not thought to be particularly outstanding, but wow, here it is. I don't have time to go into these, other than that one of the things that came out he did in that year is the mass and energy equivalence. Of course, having accomplished that, he now is a prestigious professor at the age of 41 in the University of Berlin. However, when the Nazi persecution started in Germany, Einstein came to the U.S. in 1932, became a U.S. citizen in 1940, and passed away in Princeton, New Jersey in 1955. I never had the opportunity to meet him, but I'm sure that it was a memorable experience for anyone who did. Okay, so enough storytelling. Let's get down to the job here of proving E equals mc squared. So I'm going to show you a little sort of cartoon of how we're going to do it, and then show you what we have to know, because some of you may know it already, or for those of you who don't know what you got to know, you'll learn it. So we're going to start with a hollow cylinder of mass m and length L, and it's at rest. Okay, just imagine something sitting out there in empty space, and it's hollow. And down at one end, we're going to put a source of light. It's going to emit some light. This light's going to go down the cylinder and get absorbed at the far end. Okay? So what's going to happen is the source will emit a pulse of light with an energy content E. The cylinder is going to recoil backwards to compensate for the light. So the light goes this way, and the cylinder is going to move a little bit that way. So just to give you a visualization, okay? That's all you got to think about to solve this problem. Okay? So have we got it? Have we got it? Raise your hand if you got it. Okay. Well, we got to do better than that. Let's try it again. Okay. So we got a thing here that emits some light. Just boop. It's going to be a pulse of light. It's going to come out, travel down to the far end. And if you're paying attention, it's hard not to focus on that, but you notice that the cylinder moved a little bit in the backward direction. In fact, that line marked where the cylinder was initially. And that brings, because the little bit of force that the light exerted when it left pushed the cylinder that way, and then there's an opposite force when the light bangs in down here, and it brings everything to a stop. Okay? So that's it. That's what we got to figure out. Now, of course, you can't prove that much with a picture. You got to know something to add to that. And so the question is, what are you going to have to know to do this proof? Well, the first thing I think is pretty obvious. A system with no external force acting on it does not change its motion. So if you're standing still or moving in a uniform direction and nothing there's no force applied to you, you just keep staying in the state you're in. Now, for every force, there's an equal and opposite force. That goes back actually to Newton. So you could say, here I'm standing on this floor, and gravity is pulling me down towards the center of the earth. But fortunately, the floor is exerting a force on me that's equal and opposite to the gravitational force, so I stay here. I don't drop into the center of the earth. And that's true for every time you exert any kind of a force, there is an equal and opposite force exerted on that. And I'll be showing you some examples of that. Because the forces we're going to talk about are really simple. The forces we're talking about are, we call them impulses. But what they are is they're really just like a push. They're the kind of force like a push. So they're pretty simple things. They they last for a very short time. So this force will change the velocity of the object it's applied to. So v final, that's the velocity the thing ends up with, the velocity it was starting with before you put the force on it. So that change in velocity is equal to how strong the applied force is, divided by the mass of the object. So that's not very surprising. If you push something that's light, it moves a lot more readily than if you're trying to push something that's really very, very heavy. Just if you, I don't know if you remember Newton and the story of the apple falling out of the tree. You had to understand that the force on the apple that made it fall to the earth was exactly the same as the force that the apple exerted on the earth to attract it towards the apple. Of course, their difference in mass is pretty considerable. So one moves, and the other, you can hardly see at all. So another thing to understand is that the force and the change in velocity are in the same direction. So let's get a nice physical example of that force. So we got two guys, Mo and Sam, and we'll call them a system. So there's nothing acting on Mo and Sam. They're treated as a system. Of course, gravity's pulling down on them, but fortunately the ground, or in this case I have them on ice skates on a pond, so gravity's pushing up on them, and there's no net force. So they're standing still on an icy pond, both wearing ice skates. Mo gives Sam a push, and I want you to note that Mo is heavier than Sam. So I'll bet you notice Mo moves slower than Sam, okay? And and the reason for all that, let's just take a look at it again. So there's a force, which I tried to show. Mo pushes Sam, and is probably a little surprised that he moves backward. But now we know why that is, because the force that Mo exerted on Sam acted back on him and made him move. The force was the same strength as what he exerted on Sam, but it's in the opposite direction, so that's why he went that way. And because he's heavier, he moves slower. Okay? So the thing to understand from this, and if you don't get it the first time, we'll get it in another minute. The force is inside a system, and you can treat Mo and Sam as a system. The forces inside that system that can create motion will always lead to an effect that gives you an equal and opposite motion if we take account of the masses of the things that are involved. So the force, the velocity that Sam went that way with was equal to the force divided by the mass that Sam has, whatever it was. Now, there was a force that acted back on Mo and got him moving in the opposite direction, and his velocity, of course, force is the same except opposite direction, and we have to divide it by, to get his velocity, we have to divide by his mass. So if I take the mass of Sam times the velocity of Sam plus the mass of Mo times Mo's velocity, if I take for the velocity of Sam and put this in, this mass here cancels that, and I have that I just get an F here for this quantity. When I go and work on Mo, I get, again, Mo's velocity, Mo's mass will cancel here, and the velocity that Mo has is proportional to minus F, and the sum of those two things is 0. So that's an important thing to realize, and it's true for all internal forces. This is just an absolutely general thing that we just sort of demonstrated in a particular case. So everything okay so far? Okay. If you don't stop me, I really go wild. So here we are again with Mo and Sam, just seeing it again. And so here's just the equations that we have. The product of Mo's mass times his velocity plus Sam's mass times Sam's velocity has to equal 0. And that just says that that product, Mo's mass times Mo's velocity, is the negative of Sam's mass times Sam's velocity. So now we're going to go to the case that's really crucial to understand it. This is the physics that allows you to solve the problem. So we got two guys standing on a cart, and I want the cart to be, in a sense, massless. Let's not worry about the mass of the cart, and there's no friction. So it could slide readily in whatever direction or the forces that are applied to it. So these guys each have mass m, and the guy on the right, too many buttons, here we go. This guy, he's holding a ball, and the mass of that ball is also m. That's just makes the arithmetic simpler. I realize it's pretty heavy, pretty hard to have a ball that's as heavy as you are and to do something with it, but that's the way it goes. So the mass over here is 2m, and the mass at the other guy is just plain m. Now, if I was thinking about a seesaw, I wanted to put these guys in balance. I was going to do a demonstration with a balance, but I found that I just kept dropping everything, and it would really be a distraction to all of us if we tried to pull that off. So where is the balance point? Well, I have them standing 30 feet apart, and I think it's pretty clear that the balance point would be 10 feet from the guy that's 2m and 20 feet to the guy that's just mass m, right? That's the way you would balance that, that system. And let's now see what's going to happen. So here they are again, same thing, same story. Now I want this guy to throw the ball down to the other fella, and I want him to catch it. So of course throwing that ball exerts a force on the cart, so the cart's going to move, right? And this guy is going to end up catching the ball. Now the force that this guy had to apply to move the cart is exactly equal and opposite to the force this guy gets when he catches the ball. So when this guy catches the ball, the whole system stops. Let's watch. Okay. Looks totally reasonable, except being able to throw a ball that's as heavy as you are at a straight line to another guy and have him catch it is really pretty tough. But hey, this is graphics. So now the question is, where is the new balance point? Well, we know the answer to that. It's now going to be 10 feet away from that guy, right? So that's where it is. And lo and behold, the balance points are in exactly the same place. Okay? So the thing, the distance that this thing moved, you can see what happened is the cart, with just when the ball's in the air, is just 2m. So it moved 10 feet while the ball moved 20 feet. And so, but the net result was that the balance point stays in exactly the same place. Okay? Now, I want you to answer me. What would happen if the ball was lighter? Yeah. Somebody said it wouldn't move as fast. Yeah, exactly. So you could see that the amount that this thing moves actually depends on the mass of the ball. Of course, that is assuming that the guys keep the same mass. So this is a way of measuring the thing that's moving. And I wonder if that's what Einstein thought when he thought about this model. I'm going to take some light, and I'm going to fire it from one end of my cylinder down to the other end, and the way things move is going to tell me how much that light weighs. Huh? Good idea? Are you with me? Yeah. Well, no, let's hear some younger yes. Yeah. Sure. Pardon me? Sure. Exactly. That's right. The ball is moving freely with the velocity it was thrown with.
But I mean, also the cart is sliding freely.
No, the cart, when the guy, if you throw the ball that way, you have to exert a force back this way. Right. So that's what's making the cart move in the in that direction.
So when the guy catches the ball, doesn't that something have a mass that's stopping the ball?
No, he's there and he catches the ball. So the ball exerts a force on him that was exactly the same as the force that the ball was thrown with. So,
Isn't there a gravitational force?
oh, now see, in this, I really cheated gravity, and the dead giveaway was I put that ball in a totally straight trajectory. And, of course, gravity, I want these wheels on the cart to be frictionless, so gravity and the force of the floor are all balancing out. Okay, you bet. Okay, so that's the key. This throwing things from one end to the other in a situation allows you to figure out how heavy the thing that's moving actually is. So, whoa, the balance point is the same place. Okay, so now I don't think we need to know that. Let's just go to the bottom of this slide. And now we have a problem. We know that light has energy. I mean, you step out in the sun and it warms you up. You stand by a hot fire and you feel the heat radiating into you. So light has lots of energy, and it's easy to measure how much energy it has. You just take some object, you know how heavy it is and how it absorbs light, and you see how much the temperature of that object goes up, and that tells you how much energy the light put into it. But does it carry momentum? Well, when you step out into the sunlight, you don't feel like a wind or anything hitting you, so it's pretty clear that if light has momentum, it really doesn't have a great deal of momentum. And so electromagnetic theory told us what the answer was, but you know, it's always good to demonstrate things by experiment. And unfortunately, measuring the momentum carried by light is a little too hard for me to carry out without apparatus that would be readily accessible to me. So I'll show you how it's done. So you take, this is a thing like a hair, a fiber, and this object is called a torsion pendulum. So you have a fiber, and there's a mirror, very light, two very light mirrors, just one on one side. This one on the other side is just to balance that so that the thing stays in balance. And you shine light on it. Now the light, of course, because it's a mirror, gets reflected off, and that causes this thing to turn. And you know how much force it is required to turn this fiber. And so the fact that the light comes in, hits this plate, gives it one shot of momentum, and then when it leaves, it gives it another shot. So the amount that this thing is deflected is equal to twice the momentum carried by the light. And you can measure the energy content of that light, and you measure how far it twists this thing, and you find that the momentum carried by light is equal to its energy divided by the velocity of light. Okay? That's going to be key in our proof. Yes?
If you were actually doing a physical experiment, how light would you have those?
Oh, that's a good thing. They're about as light as you can make them. So they're milligrams, and the torsion fiber is about the finest you get. And the thing that's to me surprising when I went through the arithmetic, because I was hoping maybe I could show you, is you really need to be able to focus probably 1,000 watts on the mirror to get a good measurable deflection.
What did you say the weight of the mirror would be?
Milligrams, yeah. Yes. Yeah, so they're very light things. And you also would have to do it in vacuum. The problem you would have if you don't is the energy in the light heats up air, and that totally screws up doing the measurement. Pardon me?
What material would you use?
Oh, I was planning to use aluminized mylar. You're welcome. I don't know whether it would have worked, but but I don't know whether what I was planning would have worked, but it was measured in 1905 by a couple of guys. Their biggest problem was probably getting a good vacuum in their bell jar. Yes?
Is that the principle of a radiometer?
If you do a radiometer, you reach the opposite conclusion, because a very funny thing happens. The radiometers that are typically used are white on one side and black on the other. So you think of the white as reflecting the light, But the black part of the radiometer, what happens there is that it heats up due to the light. So an atom comes in, gets absorbed on the surface, and is then emitted off that surface with a higher velocity than it came in with. So you just go in the opposite direction when you do it in air. Have to be really careful. Okay, so we now know that thing is, so now we're ready to go. We know everything we need to know. There it is. Right? Mass M, length L, light source. There's the light. Here's the absorber. Go. Moves. Okay. The light pulse has energy E and momentum E over C. Okay? Now, as a result of equal and opposite forces, when the light left here with momentum E over C, that cylinder had to go back in the other direction with a mass, and I was really kind of fussy about this. I took the original mass of the cylinder and took away the mass that the photon carried away. It's not really necessary to do that because that mass is so small that it's really negligible from that perspective. But that sum of the mass times the velocity plus the momentum of the light has to equal 0. How long did it take? Well, the time is pretty clear. The velocity of light is always c in vacuum, and so that time is just the length of the cylinder divided by the velocity of light. So the distance traveled by the cylinder is just what the velocity of the cylinder was times the time. And the velocity of the cylinder is equal, we move that over to that side, so that gives me minus E over C, and then divide that by the mass of the thing we're calling, that is the mass of the cylinder minus the mass of the light, and multiply that by L over C, which is the time that it took to get down there. Okay, so far, pretty straightforward. So, now we know the light traveled a distance L, and the cylinder traveled a distance D, and that product of how far they moved times the mass of the cylinder times how far it moved has to be 0. So it's the same balance. So we're looking basically that the balance point did not move. So if we put in the expression here for the distance that the cylinder moved, this cancels with the mass right there, and we have E times L and C times C, so we have E times L over C squared. Now if we take an L out of that, both of those, we have M minus E over C squared, that whole quantity, times L equals 0. Well, we sure know L isn't 0, so we have shown M is equal to E over C squared. Yay! So, wasn't that pretty amazing? Yeah. Of course, I mean, the guy who did it first was a genius. So it is, to me, just an absolutely remarkable achievement. Did you follow that? You're just smiling. Sort of. Okay, well, that's not bad. It's a good start. So what? Did I hear something? Lady.
Yeah, I was wondering, is that how he did it? With the...
Oh yeah, he did it with a cylinder, yeah. Well, he did it in a way that was a little more complicated because he had the light go down and then he had it come back. And that's an unnecessary step, but hey, Yes?
How far could that cylinder move that would measure it?
Pardon me?
How far could the cylinder move that would measure it? Or is that just
Oh, I mean, that was the beauty of it. You could never measure it.
a thought experiment?
Yeah. Yeah. So, I mean, it was a total thought experiment. And that's what's so beautiful of it. He just, that simplicity and clarity. He just used things that everybody knew, but put them together in a way that the result was just astounding. Okay, so what did we learn? Well, E equals mc squared, or if you like, m equals e over c squared. Take your pick. And that energy and mass are really manifestations of the same thing. Now, what did it mean physically? Well, that meant that the source of light, whatever it was, somehow has lost mass. Now, that light could have been an excited atom that de-excited and emitted the light, could have been a nucleus that emitted a gamma ray that went down to the other end, or it could be actually the power stored in an electric battery that made a flashlight beam, and that was chemical energy that had to basically go into generating the light and would have to suffer that loss of might. So it's really an amazing thing to see that what this relation is, and it really leads you to look at things in a rather different way. So, the conversion of mass into energy usually doesn't mean that you annihilate the mass and it's gone. Not every time. I'll show you the example where it does. It usually involves just a transformation of the matter into a lighter phase of matter. So if you took the chemical process that's supposed to be causing all this difficulty in climate change, a carbon atom uniting with two oxygen atoms when you burn coal to make carbon dioxide, and that generates a little bit of energy. If those of you who may know the scale, it's a few electron volts of energy. But in terms of joules, what we're talking about tonight, it's an extremely small number, 3 times 10 to the minus 19. Now, and what does that mean? Well, that means that this combination of a free carbon and 2 oxygens is lighter, is heavier than the CO2, which is lighter, and that's what allows that process to actually take place. If you want to separate those two things, you have to provide, provide energy. Now, in the case of what happens in nuclear reactors and in nuclear weapons is a neutron is incident on a very heavy nucleus, say something like uranium. And as a result of that, the uranium breaks into a couple of heavy fragments with the emission of some neutrons, and this, of course, is lighter than the neutron plus the uranium. And the energy release in that case is almost 100 million times greater. So that's the reason that you get lots of energy out of nuclear processes, is that the mass changes that are available to you allow the generation of a great deal more energy. Now, again, it's that this combination, neutron plus heavy nucleus, is lighter than what the final products are, and in that case by an appreciable amount. As I said, typically 100 million times more than is available to you in a chemical process.
The difference is the energy that's released.
Yeah, this is the energy.
The energy that's released because it's lighter.
Yes, exactly.
So it becomes lighter.
Yeah.
It becomes energy.
Yeah, so if I pardon the expression, I drive high school teachers crazy, but if I weighed this and weighed that, and compared it to the weight of the initial state, it would be lighter. And that's where the energy is coming from. Yeah. So, now there is a case where the matter just disappears and you get pure energy. If you have a particle and an antiparticle and you collide them together, they can just go into pure energy. An example is if you take an electron and collide it with a thing we call a positron, which is an anti-electron, what you get are two photons, that is two pieces of light. So there the mass has disappeared and you have pure energy. So if you with a handful of antimatter, you could create a good deal of difficulty. And those of you who have thought a bit about the origins of the universe, we say it comes from a thing called the Big Bang. And in that case, you would have thought that matter and antimatter were created equally and somehow just would have annihilated and gone back into pure energy. But there's something, physicists don't really understand it quantitatively. They understand what has to happen, but they don't know how to make it actually work. You require a violation that allows antimatter at a very slow rate to be converted into matter, and that's why the world that we live in is a world of pure matter, fortunately for us. You could see the consequences if there was a lot of antimatter around. Yes?
You said the light. Doesn't the light have some mass to it?
Well, it certainly has energy. And of course, by the fact that it has a momentum, we could then associate a mass with it. But the important thing is if you weighed those two electrons and converted that mass, that weight to energy, and then you measure the energy of those two photons, you would see you get exactly the same number. Okay. Ooh. So just a little bit of local history. I hope, I'm not good, I'm doing okay on time. Some local history. Actually, New Mexico has played a big role in this game that some of you may be aware of. Einstein was not really a very political figure at all. He was much loved and highly revered, but he did take one thing quite seriously. At the urging of many fellow physicists, but most specifically Leo Szilard, he was in 1939 to write a letter to President Franklin Delano Roosevelt, pointing out that this possible nuclear energy source, had important implications that the United States should pay attention to. What he, of course, is alluding to is he knew enough of the scientific capability of the Germans. Excuse me?
Yeah, excuse me, when do he write this letter?
Pardon me?
When do Einstein write this letter?
Oh, the letter was written August the 2nd, 1939. Excuse me. And so he was well aware of the capability of German physicists. And apparently something that I didn't know till I read this letter is that Germany had just occupied Czechoslovakia, and Czechoslovakia was one of the world's important sources of uranium. And once the Germans took over Czechoslovakia, all sales of uranium from Czechoslovakia ceased. So Einstein had a feeling that perhaps they were going to pursue developing this nuclear bomb, and he suggested to the president, I was surprised in many ways how concrete the suggestions were, appointing a person to head up a program that would lead the United States to develop such a weapon. And of course, the person that ended up being selected to do this was Robert Oppenheimer, the first director of the Los Alamos laboratory. And obviously, the president heeded this advice, and the United States launched into a thing called the Manhattan Project, and before the end of World War II, had developed a nuclear weapon. And of course, this whole development has led to the existence of the Los Alamos National Laboratory. And in fact, the first nuclear weapon that was actually fired in New Mexico, down in White Sands, some few months before the weapon was actually used. So I thank you for your attention, and it was a real pleasure talking to you.